ions. It looks really hard as far as like the stuff you have to memorize. Don't be scared though, okay? If you just trust me. They have a quiz over this on 8/29. But if you know that little poem, then you'll be good. So it goes, Nick, and then the little bitty words like the, they don't help you. It's not a poem, it's a sentence. Nick the baby camel had, and had doesn't count, had a, that's not part of it. Clam supper in, in's not part of it, in mix. Okay? So let me tell you how this works. You already have the poem, but let me tell you how we're going to use it. So rules are to get, like you see nitrate on that list, like nitrate is going to go with Nick, okay? So how that works is the consonants, which are non-vowels, equal the number of oxygens, right? The vowels, just write this on the side, like you see that right-hand side where you don't have anything, you can write it right there if you want. Vowels equal the charge. And for the ones that go with this little saying, it's going to be negative. Most of the charges for the things on that sheet are negative. There's only one positive one, it's the ammonium. These will give you the 8 polyatomic ion. And okay, so what am I talking about? So do you see on the list, it's alphabetical, do you see nitrate? When you use this way of this little saying, what it's going to give you is the answer to the one that ends in 8. Down below it, do you see nitrite? That ain't the one it's going to give you the answer to. So if it ends in ite, oops. If it ends in ite, then you'll need to take, you'll need to remove an oxygen. If this doesn't make sense yet, it will soon. And if it begins in per, like do you see, I think there's perchlorate on there. Look at chlorate, ClO3 1 minus. See per, it's got 4 oxygens, going add oxygen. Per is add an oxygen. So far so good. So you don't need to know anything yet. So these are like the ground rules, and I'm going to show you how to do it now. Alright, so we're back. So let's do nitrate. The N is for nitrate. Then I have 1, 2, 3 consonants. So that's 3 oxygens. And I have 1 vowel. That's how to figure out nitrate. Now, do you want me to do it again? I have 1, 2, 3 consonants, and I just told you to write down the consonants for the oxygen, right? I got 3 oxygens, and I have 1 vowel. So the charge is 1 minus. The charge is going to be negative on the ones you have to memorize. Do I need to do it again? No. Okay. So, like, when you go to take your quiz and it says, give me the formula for nitrate, there it is. If it says, give me the formula for nitrite, then you're going to have to go NO2 1 minus. The charge stays the same. You just got to take out an oxygen, okay? And that's on your paper. But, anyway, baby stands for bromate. It's the only BR you have. So BR is for bromine, and I have 1, 2, 3 oxygens because I have 3 consonants, and I got 1 vowel, charge of 1 minus. So we've already covered nitrate, nitrite, bromate. Bromite would be BrO2 1 minus. You just take 1 away. So that's 4 of them. You can check them off if it makes you feel good. Camel is for carbonate. Notice I have 2 C words. I have camel and clam. Camel is for carbonate. Don't have an L in it. And then clam is for chlorate. That makes sense, right? All right, cool. So 1, 2, 3 oxygens, and then I have 1, 2 vowels. Bam. There's not a carbonite. They actually make like phone cases, I think, but that's not, doesn't apply. So this right here is going to be your chlorate, ClO. 1, 2, 3 consonants, 1 vowel. Chlorite is ClO2. Perchlorate is going to be ClO4 1 minus. Rocket science. Supper. 1, 2, 3, 4 consonants. S is for sulfur. 2 vowels. That takes care of sulfate and sulfite. Phoenix is for phosphate. There's your P for phosphorus. 1, 2, 3, 4 oxygens, because 4 consonants. And then you got 3 vowels. And then phosphate's PO3 minus. That's just easier one. Yeah. Now you got to know this little saying or you're really up the creek. But basically, I know there's some that's not in the saying. I'm about to talk about that. What was your question, Casey?
What is
ITE? So if something ends in ITE, that means, just kidding, don't freak out. If it ends in ITE, you need to remove an electron because this is what the saying gives you. The saying gives you the 8. Okay? To get the I, you got to remove an electron. You got to remove an oxygen to get the per. You got to add oxygen. That makes sense now. Any other questions? Let me show you the ones that aren't on the. So there's like 4 that aren't in the saying. So those 4 that are on the list, you can read. So the first one is ammonium, NH4 plus. There's no fun way to remember that. Just you basically have to study 4 things. So that's on the list, ammonium, in alphabetical order. I think the next one's acetate. There are 2 formulas for acetate. If you look carefully, they're the same. If you do the math on the numbers of things, just do this one, C2H3O2. Just do that one, okay? Just do that. The second one, if you like choo-choo trains, go for it, but thank you for laughing. That's easier. When you get to AP, you'll understand why it's written out the long way. It has to do with the position of the atoms, how they bond, but that's going to be beyond our scope. Anyway, the other one would be cyanide. Cyanide's easy. Cyanide. Because it looks like the word, like cyanide, right? Ammonium's the only positive one, okay? And then the last one's hydroxide, which you probably already know from acids and bases, maybe. That's what when we put the lithium and sodium stuff in the water and it turned purple, like that's what was doing it, the hydroxide. The water was getting split. Look, you don't even have to use your imagination. Here's water, Mickey Mouse. The water was getting split and one of the hydrogens was ripped off. And this got together with another hydrogen and made hydrogen gas. Anyway, that's hydroxide. And that's the 4. These are not in, they're not in the poem. Okay, you're just going to have to, so you got to say 4 things and a saying, and you should be good on the quiz. I'll try to bring them up and do some studying here and there, but I make no promises. And like basically, if you know your elements and you pass those quizzes and you pass this one, it's like you've learned your alphabet and now we're about to learn how to spell. If you don't know these, your life is going to over and over and over again and be less than optimal. Okay, so you can put that to the side, get your new piece of paper, and we're going to start talking about what we did outside. Yeah. Okay, so what we just did outside, you can write this at the top of your paper. This is bonding and electronegativity notes. Don't put your polyatomic ion sheet up because if you flip it over, it has a periodic table on it with electronegativity values. And then you should put today's date because you already figured out yesterday that I take up notes sometimes. Some of y'all didn't take notes, which I don't understand, but that's fine. You do you. Okay, so there are 3 types of bonds that we have discussed today. We played tug of war 3 times, except for that time y'all lost, so I ain't home to get to. So the first kind of bond is ionic. And so this is the only bonding involving metals, which is when y'all played, this was the only time the boys were in there. By the way, in my 12 years of doing this, that's the first time the boys have lost. So.
We're outnumbered and outweighed.
Okay. So this is the only bonding involving metals, and it's basically going to be a metal plus a nonmetal. And what occurs is the metal's electron, and it could be more than 1 electron. It could be 2 electrons. The metal's electron or electrons get removed by the more electronegative. Can I put down En for electronegative? Non-metal. My pen's starting to get a little lazy. That's not me, that's the pen. So, by the more electronegative non-metal. So that's what happened, right? When we played tug of war, the rope was the electrons. The more electronegative side, the girls. But I'm going to keep referring back to this tug of war, and just from like memory, I'm going to accidentally say boys, but y'all just remind me. Especially the girls. Girls continually remind me that y'all won. So, when that happens, you get ions created. Now, so I'm going to draw that for you. If everybody's, I'll let you finish writing. So, while you're waiting, you can go ahead and draw a lithium atom and its Bohr model. You can just put a plus sign in the middle. You don't need the exact number of protons. That's not important right now. So, yeah, let me show you what happens. I'll turn off this light. Oh, well, that's too many lights. Tell you what, Aki, go turn on the right-hand light. Thanks, boss. All right. So here we go. If I draw a Bohr model for lithium, lithium has 3 electrons. 1, 2, 3. It has 1 valence electron because the outer shell has 1 electron, but also because it's in group 1, and that's an easier way to remember it. So here's lithium, and this is lithium, the metal, the atom, not ion yet. And then I have fluorine. Fluorine is going to be smaller than lithium, right? Because the size decreases as you go across, and it's going to have a stronger positive pull from the nucleus. So it's going to be that's not really smaller. I could do better. I believe. There we go, better. And so it's going to have 7 valence electrons. 4, 5, 6, 7. And because it's so electronegative, what's going to occur is this electron will be removed from the lithium and be added to the valence shell, the outer circle, the valence shell, the outer energy level. Be added here. And now, when this occurs, lithium will now have the electron configuration of helium, which is stable, and that's what they're trying to be like noble gases. I mean, I'm not just telling you that, I'm obviously telling you why. And then fluorine, at this point, will have the electron configuration of neon. So what happens is this becomes Li plus, and then I have my 2 electrons here. Probably should, I'm going to stick with my same colors, not to confuse the children. So 2 electrons in the first energy level for lithium. And then fluorine now becomes what's called fluoride. Y'all heard fluoride is in your toothpaste? Yeah, why is that? Why is it called fluoride? Well, the reason it's called fluoride is because it's an ion. And when things become anions, or they're the second word, I'll show you that in a second, you drop the end and make it "ide." So hang on. 1, 2, 3, 4, 5, 6, 7, 8. Now, this is called lithium fluoride. As far as why I make it fluoride, don't stress. I'm going to teach you that, okay? So that's lithium fluoride. Now, what's happened here, I have a positive ion and I have a negative ion. So, turns out they stick together. Like that's actually, this is exactly what it looks like. See that? Look. Yeah. And so, they don't just stick together like this. They actually stick together in a big old cube like that. That's what it really looks like. And so, if you put, like sodium chloride, right? That's ionic, metal, non-metal. If you put salt in a pan and you cooked it as hot as you could, do you think it'd ever melt? Can you imagine salt melting? It melts at like 3,000 degrees, but you ain't gonna get it to melt. The reason it ain't gonna melt is because it's stuck. Each ion is stuck to 6 other ones. Because the cube has 6 sides. Y'all hanging with me? Alright, anyway, so that's lithium fluoride, and they're stuck together with the electrostatic attraction of the positive and negative ion. So this is what ionic bonding actually looks like. It's a transfer of electrons. It's cation, anion, metal, non-metal. So far, so good? So there's math to this. It's not hard though. So I want you to look on the back of that polyatomic ion sheet, and when you look, there's values for electronegativity. So look at the electronegativity values of lithium and fluorine, and then I want you to subtract them. So it's 4 minus something. I don't recall.
1. It's 3.
4 minus 3?
No. It's 4 minus 1.
I'm about to say, like, I don't think that's right. I don't mean that you do. Okay, so, dun-dun-dun-dun. When I go to do the math, fluorine is the most electronegative element, and then lithium's electronegativity is 1, and I get a difference of 3. So, of course, lithium would, when they play tug of war, like lithium would be able to steal the rope, it has 4 times the electronegativity that lithium does. So, the difference in electronegativity here is 3. And so the definition of an ionic bond is greater than or equal to electronegativity difference of 1.7. Now, when you subtract them, difference means subtract, right? This is a gray area. Some books say 2, some books say 1.6. We're going with 1.7 as a chemistry department here at Hillgrove, and just realize it's on a continuum. Like, it's not like I'm a metal, I'm going to be ionic. Like, it's on a continuum. But that's what you need to know. So when you subtract them, if you get a number that's equal to or larger than 1.7, it's ionic. Okay? So that's the first time. That's when the girls played the boys and the girls won because they were the non-metals. Next. So the second type of bond that I would like to talk about is, what happened next? Oh, polar covalent, right? So the polar covalent is where you have 2 nonmetals sharing. There are no ions formed. There's no transfer of electrons. One atom does not take all the electron. It just basically moves a little bit towards it, sharing electrons. But they're shared unequally. So that is to say that one is more electronegative because one is more electronegative than the other. So this is what I was talking about with water, okay? Oh, and the electronegativity difference is, notice, you know how numbers work with the alligators? Yeah, okay. It's between 0.5, so not equal to 0.5, okay? Between 0.5 and 1.7, but not including those numbers. So 0.51, yeah, polar. 1.69, polar. So not including these numbers. Not equal to. Greater than 0.5, less than 1.7, but not equal to. Okay? Doesn't have the equal sign on the bottom of the alligator mouth. Alright, now let's prove that water is indeed polar covalent. So I would like you to show me that a hydrogen and oxygen bond, do the math, is polar covalent. Hydrogen's a nonmetal, so when you go to do some practice here in a minute, I know it's left of the metalloid line, but it's a nonmetal. So go ahead and do the math. I'm sitting down like it's going to take you a long time. Yep, that was a good break. All right. Good game. Let me scroll down a little bit. What did I say? I told you to find the electronegativity difference of hydrogen and oxygen. And, of course, that's on the periodic table. Everybody's, like, following along with that, right? So, hydrogen, well, let me start with oxygen. So, you'll start with the non-metal because it'll have, or the bigger number. You're just finding the difference. So, it's 3.5 is oxygen, right? Minus 2.1, and that gives you 1.4. So, it does fit our definition of polar. Now, listen, I have some little Mickey Mouses here, and we'll play with these later. So, this is what water looks like. So So water looks like this. It's little Mickey Mouses. And, I mean, okay, that was a terrible demonstration. So they do stick together, okay? So they're stick together, but they're not as stuck as those are. But basically, liquid water does this. It's kind of in constant motion, but the Mickey Mouse ears and the chins are kind of temporarily stuck. And so that's why if you do a belly flop, you have to break these apart. And the reason that you have to break them apart, let me show you. Let me do red for oxygen, and then I'll do black for the hydrogen. Don't freak out, this is just a little Greek letter. But this side, this is a negative dipole. You basically make an 8, you don't connect it. This is the negative side, the chin is the negative side of Mickey Mouse. Because oxygen is more electronegative. Yeah? So when they put the tug of war, that's the side that almost wins. When the girls were playing and I had to stop them, that was the oxygen that was pulling too hard. Okay? And then this side is positive. So anyway, when you do a belly flop and it hurts, it's because those dipoles are basically stuck to each other and you have to break them apart. And that hurts because it's almost like a solid surface at that point. Anyway, this is also why it's hard to boil water. You know when water boils, it doesn't make hydrogen and oxygen. That would blow your house up. Y'all realize those are both flammable, right? So little Mickey Mouse just goes floating off into the kitchen. And then they rejoin to make droplets on the underside of the microwave, and then it drips down, and that's gross. You know what I'm talking about? Yeah. That's how water boils, and that's why it sucks to make spaghetti. Life mysteries with Miss Freeman. Moving on. Next is nonpolar covalent, and so this is, again, two nonmetals sharing electrons. Again, we're sharing, we're not taking. Covalent. You know, covalent sounds like cooperate, like it works together. Nobody takes the electrons. Two nonmetals sharing electrons evenly. Or mostly evenly. It doesn't have to be perfect. And so the electronegativity difference here is 0.5. It's less than or equal to 0.5. Difference. Not just electronegativity, but the difference. Okay? And so, here, okay, you ever taken like solid butter? You just throw it in a pan and it melts like that? Do you know how like oil and butter, like they don't mix with water, right? They don't. It's because water's polar and fat is non-polar. And these don't stick together because they don't have a positive side and a negative side because they ain't an atom pulling on the rope harder. So they melt very easily. They boil very easily. Girls, y'all ever done your fingernails and you take off that nail polish? You know how fast that evaporates? Guess what? It ain't very polar. So that stuff doesn't stick together. And that's why you can smell it so much. Because it just is floating around the air. Easy peasy. Not stuck to its little friends like water is. That's some AP level stuff. Dude came back from his phone again. That's funny. Open the door. So anyway, let's take a bond like, I'm trying to think of a non-polar bond. Let's do carbon and, well, that's easy. Do carbon and selenium, right? What if carbon and selenium bonded? Tell me the electronegativity difference in that. It's right there. Yeah, is it 2.5? Behind 2.5 minus 2.4?
No. Wait, no, I was looking at this game. Oh, it's 2.4.
Okay, so carbon is just slightly more electronegative than selenium, so you can see how really no strong poles form. So do you get it? Kind of easy, right? I mean, this isn't easy, but I tricked you into thinking it is. So yeah, so that's it. That's all the things. I'm gonna go ahead and hit this button.